Good afternoon and happy St. Patrick's Day to you. Corey, our presenter, he should be sharing his screen momentarily, but my name is John Kowalski. I'm part of the marketing team here at Gardner, and welcome to Office Hours. If you're unfamiliar with the Office Hours format, this is a shortened presentation, maybe 20, 25 minutes, followed by open discussion to address any challenges you may be having at your own facility, answer any questions, things like that. So if you have any, please log them in the Q&A box located in the bottom right-hand corner of your screen, and we'll get to them in order. And also take note that we are recording this, and through some follow-up email activity tomorrow morning, you'll get a link to this recording as well as the presentation that Corey will be showing. So with that, let me introduce our speaker, Mr. Corey Cohen. He's our Senior Application Specialist at Gardner. And with that, thanks for joining us. There you go, Corey. It's all yours, sir. Are you still muted, Corey?
You all can.
You there, Corey?
Can you hear me?
Now we can. Welcome. It's all yours, sir.
All right. Thanks, John.
Yeah.
And hello, everybody. Thanks for coming. So for today's office hours, we thought we would go through kind of an overview of the different types, the different categories of color instruments that we make and sell, and just sort of what what the use is for each one. So as usual, the presentation will be fairly brief, and then when we finish, we'll have some time for some questions so we can get more into detail if you want to hear about any one of these instrument types, so we can get a little more into detail on them. So to start out with, we're going to talk about solid color measurement. So by solid color, we mean basically anything that only has absorption pigments in them. So absorption pigments are just pigments that make things a certain color. We're not talking about effect pigments right now, like metallics or anything like that that cause a sparkly effect, just regular, plain old colored material. So that's what you would use one of these solid color instruments for. So first of all, why do we care about color? Color harmony is important because customers consider they consider this important in the purchasing decision. Consumers like to buy things that they think look good, and color harmony is a big part of that. So color harmony is when you have a product that has multiple components that may be fabricated and painted or otherwise colored separately and then put together in a final product. And it's important when that happens, when they all come together in that final product, whether it's refrigerator, an oven, or an automobile, or some sort of electronic device. It's important it all looks good together. So this is why it's important to track and measure color and gloss. And light fastness is also another key criteria. Light fastness is how long a material will hold on to its color, how little or how much a material will, the color will change over time. So when you buy something in a certain color, you want it to last for years and still be that color without fading too much. But even more than that, when you have these multi-component products, you don't want different parts of that product to fade differently because then it's going to start to not look very good. Neighboring components, neighboring panels will no longer match each other. And it's not good. So it's good to monitor not only color and gloss harmony, but also light fastness. So in order to talk further about, I want to get into the different instrument geometries for solid colors. Before we do that, we have to talk a little bit about gloss. So gloss is basically how much light reflects off a surface at the specular angle. So when you have a directional light source, like in this diagram, you shine light on the surface, and a certain percentage of that light is going to reflect off at the opposite angle, and that's what we refer to as the specular angle. So for this surface here, this nice glossy surface, the observer standing at that specular angle is going to see a nice, clear, crisp reflection of that, that light source off of the surface. But now we're dealing with a matte surface or a low gloss surface, and so now when the light hits the surface, it's going to be diffused. It's going to bounce off in all directions. Not as much of that light is going to reflect off at the specular angle, and so the observer evaluating that surface at the specular angle is no longer going to see a crisp, clear, reflected image of that light source, but now that image is going to be fuzzy, hazy, less distinct, and that's because more of that light is bouncing off in different directions and is being diffused. So if we now look at these two painted panels, so each of these panels, we have one black, one red. The pigmentation is the same throughout. These were painted, the black panel is painted the same black color throughout. The red panel is painted the same red color throughout. But half of each panel was also coated with a glossy clear coat. So the only difference you're actually seeing here between the two sides of each of these panels is the gloss. The pigmentation is exactly the same. So to our eye, to the human eye, the glossy part looks darker and more saturated despite being made of the same colored material. It has the same pigmentation. So both color and gloss have a significant influence on the visual impression. So that brings us to our first geometry of spectrophotometer for solid colors, and that is the 45-0 geometry. So the way this one works is the light source is directional. The light source is shining light on the surface at a 45-degree angle. You can see it's kind of coming in this cone of light, and that's referred to as circumferential illumination. So all of the light all the way around is hitting that surface at a 45-degree angle, but it's uniform in a circle all the way around. And so the reason for this geometry, this 45-0, 45 for the direction of the light source, 0 for the angle of the detector normal to the surface. The reason for this is it mimics how we typically see things in everyday life. Typically, we're dealing with some sort of directional light source, whether it's the sun or a lamp inside our house. And that light shines, light source shines light on the object we're evaluating or we're looking at. And typically we're going to view that object at a diffuse angle, such as this 0-degree viewing angle that the 45-0 geometry uses. We don't typically look at things at the specular angle, that gloss angle, because then what we're going to see is glare, what we commonly refer to as glare. So we typically view things at a diffuse angle, and that's exactly how this instrument is measuring. Directional light source measured in a diffuse direction. And so for this type of instrument, differences in gloss and structure on the surface do lead to measured color differences, just like how we saw it in that previous slide, how the only difference here is in the gloss of the surface, but that causes us to see the two sides of each of these panels as being very different. The 45-0 instrument will also measure it in that way, where it's going to see color differences due to just differences in gloss or texture in the surface. So that's the 45-0 instrument. And then we have, and the circumferential illumination reduces the influence of directionality. So that the point of that is that you can orient it any way you want on the surface and get essentially the same results. But then we go to the sphere geometry, the other major geometry used for solid color measurement. And the way this one works is you have a light source. Instead of shining light on the sample directly, the sample that you're measuring, it's going to shine light into what we call an integrating sphere. So that light is going to bounce all around the inside of that sphere. That light is going to be diffused, meaning by the time it bounces down and hits the sample, it's coming at the sample from all directions rather than one defined direction as with the 45-0 instrument. So these sphere instruments are also commonly referred to as D8, D for diffuse light source, 8 for the 8-degree angle of the detector. So the diffused light source rather than a directional light source, and this means that differences in gloss and structure do not lead to measured color differences, right? So the 45-0 measures color as we see it, where the gloss is going to affect the color measurements. Sphere spin instruments ignore that gloss effect, and the values you get out of it will not be affected by the gloss and the structure. So then we have a third geometry referred to as sphere specs. So the point of specs was to build a sphere instrument that could also measure like a 45-0. And the way they do that is by introducing a gloss trap that traps the specular reflection and prevents it from getting to the detector. So it removes some of the light from getting to the detector in order to make a specs instrument, specular excluded, in order to make it read more like a 45-0. And so it was found that the correlation between specs and 45-0 is pretty good on high gloss surfaces, but as the gloss level diminishes, as you get to lower gloss surfaces, the correlation between specs and 45-0 also diminishes. So if we take a look at the actual measurements of the two sides of this panel as taken with these three measurement geometries, if we look at the 45-0 geometry, this is the one that measures color like we see it, we can see that in particular the L values are much different between the glossy side and the matte side. The L value is much, much lower for the glossy side. And this matches up with how we see it. We see the glossy side of that panel being darker. The 45-0 instrument measures that side as being darker. Same with the specs, the D8 specs instrument. Remember, it's meant to measure like a 45-0, at least on high gloss surfaces. And here we can see that it is. It is measuring that high gloss surface as being much darker than the lower gloss surfaces, which again matches up with what we see visually. But the D8 spin geometry, the sphere spin, specular included geometry, ignores any surface structure, it ignores any gloss, and it only measures the pigmentation. So that instrument is going to measure the two sides of this panel as being essentially the same. And if we look at the red panel, the two sides of the red panel, we see something similar. Here with the 45-0 geometry, the glossy side is being measured as darker, and it's also being measured as more chromatic. The A value is higher. It's being measured as more red than the non-glossy side, and it's being measured as more yellow also. So there's more red, more yellow overall. It's being measured as more chromatic when measuring the glossy side than the matte side. And again, this is how we see it. We see more chroma in the glossy side of this panel than in the matte side. Similarly, the D8 specs, the specular excluded geometry, measures similarly lower L value, higher A and B value. But here again, the D8 spin geometry ignores the surface gloss, and it's going to measure the two sides of that panel as being essentially the same. So whereas the 45-0 and the D8 specs measure the color as we see it, and that's reflected in the color numbers, the spin geometry, the sphere spin geometry, ignores those surface effects and only measures the pigmentation. So for that, we have our Spectra 2 guide instrument. This comes in the three geometries just discussed. It comes in the D8 geometry, which means you get spin and specs in one instrument. And it also comes in the 45C0 geometry. In addition to that, it comes with a built-in 60-degree gloss meter. Now, this is an actual built-in gloss meter with its own light source and detector. This is not a calculated gloss. This is an actual gloss measurement according to ASTM, D523, and all those standard test methods. and you'll get the same performance out of that gloss meter, the same tight precision and accuracy as you do out of our standalone microgloss meters. So color and gloss in one with the Spectra 2 guide. And that brings us to our next topic, which is fluorescence. So fluorescence, real quick, is just when a molecule or an atom, when an electron absorbs a photon. So that's what's happening in the first picture. A photon is striking this electron that's orbiting the nucleus. And because that photon is of just the right energy, just the right wavelength, that electron is able to absorb its energy and jumps up to a higher orbital. But that electron doesn't want to be in that excited state. It wants to go back to its ground state, which means it has to give off that excess energy. And it does so in the form of heat and light. So it's absorbing a photon of a given wavelength and then re-emitting another photon plus heat. So because of conservation of energy, since some of that energy it absorbed is going towards heat, the photon it re-emits has to be lower energy than the one it absorbs. And that's what's causing fluorescence. That causes something called Stokes shift, where the light that was absorbed by the electron is re-emitted at a longer wavelength. So Stokes shift is when the light is shifted from lower towards longer wavelengths. For example, you can go from UV to blue, green, yellow, red. You can go from blue to green, yellow, or red. It can absorb green and then go to yellow or red. It can never go towards shorter wavelengths, only longer. So you can never, for example, have a material that absorbs green wavelengths and re-emits it as blue. So this is called Stokes shift, and this is the essence of what fluorescence is. Fluorescence is when a material absorbs light of a given wavelength and re-emits it at longer wavelengths. So in order to measure that fluorescence effect, in order to measure the color accurately when it has fluorescence, and B, in order to quantify that, we have a couple different instruments that can do it. So here you see our full line of Spectra guide or Spectra 2 instruments, beginning with our basic model, the Spectra guide. It has a reproducibility of 0.2, which is fairly tight, but not quite good enough for us to recommend digital standards. This model also has the built-in 60-degree gloss meter, and it includes the EasyLink software, which is our simple spreadsheet program. Moving up from there, we have the Spectra 2 Go, and this one has a reproducibility of 0.1 delta E. So this one has tight enough inter-instrument agreement that we can recommend using digital standards, which is a big deal for this instrument. It also has the built-in 60-degree gloss meter, and this one includes our Smart Chart software, which is a much more powerful, much more versatile software for QC and data collection. Going up from there, we have the Spectra 2 Guide. This one also has the reproducibility inter-instrument agreement of 0.1 delta E. It also has the 60-degree gloss meter built in, but this is the one that can do fluorescence detection. So if you're dealing with fluorescent materials, you want to make sure that you can measure the color of those fluorescent materials accurately, as well as quantifying the amount of fluorescence in the material to predict color fading. This is the instrument you want, the Spectra 2 Guide. So it doesn't just do color and gloss, it also does fluorescence evaluation. It has a built-in fluorimeter to do fluorescence evaluation. And then we have our top-of-the-line model, the Spectra 2 Guide Pro. And this is the one, this has that same, actually has improved reproducibility, particularly in the low reflectance range. But this is really the one that's the specialist for doing jetness measurements. So jetness measurements is jetness is a measure of how black is your black, essentially. So if you're dealing with very dark colors or colorants, you want as little reflectance as possible. You want as good a black look as possible. This is the instrument you want for measuring jetness. And the reason you need a special instrument for that is because of the nature of jetness measurements. Jetness, since you're measuring black colors, the amount of reflectance you get off those colors is inherently very, very low. And so you really need an instrument that can measure with very, very high precision, particularly in the very low reflectance range. So you need a very precise instrument for that, and our instrument for measuring jetness is the Spectra 2 Guide Pro. So moving on from solid color instruments, we're going to talk about multi-angle color measurement. And the reason for multi-angle color measurement, the reason you might need multi-angle color measurement is because of effect coatings. And these are very common, particularly in the automotive industry. As much as 80% or more of today's automotive finishes are effect coatings, and these include things like metallic flake that cause lightness differences depending on observation angle, pearlescent coatings or interference pigments that cause a color change depending on the viewing angle, and then you have other pigments like ceralics and luxan that cause this special glitter effect. And so for that, we have the BICMAC, which has one illumination angle at 45 degrees off the normal, and then 6 detection angles. And this captures what the color looks like at a number of different angles, which is necessary for these special effect pigments. And so here I have a couple examples for you. So here is a multi-angle color measurement of a solid green color. Remember that solid colors don't have any special effect pigments in them, only absorption pigments. And we can see that reflected in these color curves. So these colors are being measured. This color is being measured at an evaluation angle of 15 degrees, 25 degrees, 45, 75, and 110. And we can see that the spectral curves are all pretty much right on top of each other. So the spectra really isn't seeing much of a color difference depending on observation angle in this solid green colors. So solid colors look pretty much the same no matter what the observation angle is or the measurement angle is. We can contrast that with a metallic green color. So this is now a color that has absorption pigments in it to make it green, but it also has little bits of metallic flake in it to give it a sparkly effect. And what that does is you can see these curves, these measurement curves at these 5 different measurement angles, they're the same general shape, meaning that the hue of the color is going to be essentially the same, but the reflectance levels vary somewhat depending on the measurement angle. And what that tells me is that the lightness level is actually going to change depending on the observation angle. We can see that at the near specular angle, that 15-degree measurement angle, that's where the color is going to be lightest. And as we get further away from that specular angle, we go through the 25-degree, the 45, 75, 110. As we get further away from the specular, that color is getting darker and darker to our eye. And this is one of the effects that metallic flake has on these coatings, is that it causes light-dark flop, where the lightness level is going to change significantly depending on the observation angle. And then we have our next example, which is a metallic silver. So this is a bit more of an extreme example of light-dark flop. So you can see, if you look at the y-axis, you can see the difference in the reflectance values here for this metallic green versus here for this metallic silver. So this color has a lot more metallic flake in it, which is going to cause a lot more light-dark flop. So at the near specular, the 15-degree angle, you're going to get a fairly light-looking color. And as you get further and further away, that color is going to get very, very dark, relatively speaking. So what that does, that light-dark flop effect, it's not a bad thing. It actually looks appealing on cars. For example, you take this nice curvy-looking Porsche here, and that light-dark flop, the change in lightness levels depending on the observation angle, it's going to cause a very pleasing look where it accentuates the curves of that car. And so that light-dark flop is going to be dependent on things like the orientation of the flake, whether it's oriented more or less in line with the plane of the coating, or whether it's disoriented, as you can see here on the right, that's a bit more oriented. And also the size and type of the flake is going to affect how much light-dark flop you get. So there's a calculation when you take a measurement with a multi-angle spectrophotometer. There's a calculation for what we call flop index, which is just a single number that tells you the magnitude of the light-dark flop as you move from angle to angle. So another effect you get with these special effect finishes, particularly like metallics and things like that, you get sparkle and graininess. So here at the top left, we can see an image of a metallic coating under direct sunlight, under direct lighting conditions, and that's when it produces this brilliant sparkle effect that's very appealing to the eye. But then on the bottom right, that's that same coating under diffused lighting conditions, which in real life is often cloudy skies. Cloudy skies produce diffuse lighting, and that causes a condition that we call graininess. So that's that sort of salt and pepper, sandy effect that you get under diffuse lighting conditions. And so in order to fully evaluate your surface, you also need to evaluate the effect pigments, the effect flake, the metallic flake in the coating. And so for that, our BICMAC instrument measures not only color at 6 different angles, but it does sparkle characterization with 3 different illumination angles, direct illumination, of course, because that's where we see sparkle, and then it does graininess characterization under diffused illumination. So it's a complete evaluation of effect colors with one instrument. All right, going on from there, we're going to talk about liquid color measurement briefly. So there are 2 ways that you can measure liquid colors. If you're talking about solid colored liquids or liquids that are more or less opaque, these are things like paints, inks, cosmetics, and sometimes food products. This requires non-contact measurement with a reflectance spectrophotometer, such as our Spectra 2 guide instrument. And in order to do that, you have to draw down the material first in order to measure it. So the second category of liquids for color measurement are transparent colored liquids. These include things like pharmaceutical chemicals, solvents, oils, transparent resins, and again, some food products. And so there are specialized scales for specific industries or materials, and there are both visual and instrumental methods available. So for these solid colored liquids, the first step in measuring those is, again, to draw it down. So you want to take some sort of standard substrate, such as our BICO charts, and they come in all different designs and sizes. You then take an applicator, such as a drawdown bar or a wire wound rod, and apply the material to the backing, to the substrate. You can also use an automatic film applicator for this. That adds an extra bit of uniformity to the sample preparation. And so once you have the drawdown, you can use one of our color or even gloss instruments to evaluate the material using a wet drawdown template. So these templates are fitted specifically for each of our instruments. And you can take those and put them on top of your still wet drawdown. It doesn't have to be dry first. You can put it on a wet drawdown and then put the instrument on top for measurement, and that will hold it just above the wet coating so that you don't contaminate your aperture. So that's for measuring solid colors. And then we can also evaluate transparent liquids using one of these methods. So one of the most common color evaluations for transparent liquids is called the Gardner color scale. It was developed in the 20s to evaluate, the 1920s, I should say, to evaluate color of oils, varnishes, and resins, and the scale goes from 1 to 18, ranging from what we refer to as water white, meaning just clear, to yellow to deep red. So one of the methods that you can use to evaluate Gardner color is this delta color comparator. So you have two sets of glass wheels corresponding to the 18 Gardner colors. So on the left, you'll have the odd numbers, 1, 3, 5, 7, 9, so on. And on the right, you'll have the even numbers, 2, 4, 6, 8, and so on. And so the idea is you take a vial, a test tube full of your liquid, and you place it into that, the empty spot in between the two sides, and then you adjust the filters until you get as close as possible to that, the color in the center, and then you evaluate it visually based on which glass filter your color, your liquid most closely corresponds to. So this is a visual evaluation for Gardner color. You can also use the liquid standards pictured here to the left. So it's a rack of actual liquid Gardner color standards going from 1 to 18. And so the idea here is pretty similar. You would take a test tube full of your liquid. There are slots above, in the middle, in between each standard tube. There are slots where you can put your test tube and evaluate it next to each of these colors until you get to the closest one. So two visual methods, the Gardner color liquid color standards and the delta color comparator, which uses glass filters. But then we also have instrumental color measurement for transparent liquids. Keep in mind this is only for transparent liquids, not for solid color or opaque liquids. But you can use, for example, the LCM4 instrument to evaluate Gardner color instrumentally, along with a few other scales, Hayes and APHA, iodine, Sabalt, mineral oil. So this one has a limited number of simple scales it can do, such as Gardner color. And then we also have the more robust LCS4, which can measure all the same scales with the addition of doing actual color scales, such as CIE, LAB, LCH, Hunter LAB. Can use the 2 or 10 degree observer. So for a more complete analysis, color analysis of transparent materials. And then that brings us to visual evaluation. So just briefly, visual perception is of course dependent on the light source. Different colors are going to look different depending on the ambient light. So colors are going to look, for example, different during, if you're outside, they're going to look different in the middle of the day than they would at sunset. Also, inside lighting is going to look different than outside lighting. You're going to deal with fluorescent lamps, tungsten lamps, more and more LEDs. So all these light sources that we use in everyday life are different. They have different spectrums of light that cause the colors that we're evaluating to look different. So in order to really properly evaluate your colors, you need to standardize the light source. And so one other reason for looking at colors under different light sources is not only will the colors themselves look different under different light sources, but if you have a sample standard pair, it's actually possible for that pair to match perfectly under one light source, but not under another. And this is called metamerism. So we can see a sample standard pair here that's undergoing metamerism, because under daylight, the two are a perfect match for each other, but under incandescent lighting or fluorescent lighting, to a lesser extent, they're actually a mismatch. So it's important sometimes to look at colors under different light sources to see whether they're going to match under all light sources and not just one. And so we have a line of light booths that provide standardized lighting conditions. For example, our BICO Spectra Standard or BICO Spectra Light light booths, and these each come with a selection of different light sources, so you can view your samples under D65 daylight, A incandescent lighting, fluorescent lighting, even UV to see if they're fluorescing. And then we have the Big Daddy light booth, the BICO Spectra Pro, not only our largest light booth, but also our most accurate light booth, meaning particularly the D65 illuminant, the daylight illuminant, the most commonly used illuminant. This is the most accurate daylight illuminant on the market, with a visible metamerism index of between 0.07 and 0.18. And what that means is just in order to evaluate the accuracy of the light source, the industry uses a metameric pair. This is a pair of colors that's going to look perfect under perfect D65 and not so much under other light sources or under imperfect D65. And so the fact that the visible metamerism index for this instrument is so low classifies it as a Class A light booth for D65. So this is the most accurate D65 representation you can get anywhere. Okay, so I think I've done enough talking for now. I'm going to pass it back to John for our Q&A.
Q&A, or I like to call Stump the Corey. That's always fun too. So thanks, Corey, appreciate that. And just note for everyone out there, we will be sending the recording of this as well as the presentation materials out in an email tomorrow morning that you'll get. So you'll have that there. So now let's get into some questions here. This is in reference to the beginning of the presentation, Corey. Can you expand on the circumferential illumination, and does that mean I can use it on a textured surface?
Yeah, so let me get back up. There we are. Okay, so this is for the 45-0 instruments, where 45 stands for the angle of the light source. So the light is shining on the sample at a 45-degree angle off the normal. But as you can see from this graphic here, it's not just coming from one direction. It's coming from all around. And so it's all hitting it at a 45-degree angle in a cone of light. And that's what we're calling circumferential illumination. And the reasoning for that is that you can put your Spectra down, your Spectra 2 guide down, and take a measurement and then turn it 90 degrees or turn it 180 degrees and expect to get the same measurement because of that consistent homogeneous light source from all around. So yes, you could use it on textured surfaces. You could still get different measurements depending on what spot you choose, because different spots are going to capture, slightly different textures, different, peaks and valleys and things like that. So when measuring textured surfaces, we always recommend doing an average. But if you do put it down on the same exact spot, you would theoretically be able to turn it any way you want on that one spot and get the same measurement.
Okay, thank you. Couple kind of related questions. What instrument would you recommend for an automotive interior color harmony situation?
So I believe automotive interior, I don't know if Ray's on, but I believe they typically use 45-0, and that's because they're often, that goes back to the color harmony part, where you're trying to match up the materials that you're, maybe fabricated in different places, and you put them all together. And sometimes those materials aren't always, those parts aren't always the same material. So you might be trying to match, a vinyl with some other type of plastic. And in that case, you want the 45-0 because 45-0 is going to see color as we see it. So if you were using a sphere instrument for that, remember those measurements we took. So a sphere instrument might tell you that two materials are the same color even when they look different because of the difference in the gloss. So if you're really trying to match up different materials in the interior, 45-0 is generally recommended. And I believe that's what most car companies have standardized on.
Okay, thank you.
With Corey, 45-0, most companies use 45-0. One company uses specs, but only one company.
Okay, thanks, Ray. Another question, what instrument would you recommend for a polished metal surface?
Polished metal. Typically, if you want to measure the color of metal, we would recommend a sphere instrument.
Okay. Question here, too. What would be a good instrument to measure the color temperature of luminaires?
Oh, so that's called a spectroradiometer. We do not make those. So spectrophotometers, such as we sell, reflective spectrophotometers are for shining light on a surface and then measuring what the material does to it. What you're talking about is measuring the spectrum of light being given off by a light source, and that's a radiometer. That's not something we make or sell.
Do you know by any chance if our partner company, Gardco, if we can source one of those through them? Do you know, Corey, or any of the field people on the line?
Not off the top of my head.
Okay. You can just reach out or go ahead.
I think
they have source.
Yeah, good.
Yeah, they have a couple of different things that would measure luminance, and there's a very wide range of instrumentation from very inexpensive, where you just get the amount of light at a certain distance, and then to Corey's point, if you want to characterize the light source, you need a spectroradiometer. So it just depends on what you're trying to do. If you're like in the photography market, they use just simple luminance meters to make sure they have the right f-stop setting and speeds for the cameras.
Thanks, Greg. So if you need more information, feel free to reach out to us. We can help you in getting one either from Gardco, our sister company, partner company, or source it elsewhere for you. Also, Jose is asking, a value of A star equals 0. Is that green or red?
That would be neutral. Neither. That would indicate like if both the A and the B were 0, that would indicate like a gray or black or white.
Okay. No color. Thank you. Another question here. So the variation you see on the 45-0 and specs is only at low gloss and high gloss being the same. Is that correct? Maybe, Ray, you can help with that question.
What's the question? The correlation?
Yeah, I think they're asking, is it only at the low gloss that you have an issue? The high gloss is the same. And you're showing the comparison right now, so I can see it on the screen, but.
Okay.
Does that make
sense? Going to correlate better at high gloss. As the gloss goes down, they don't correlate as much. Generally, we're going to recommend the 45-0 if you want to measure color as you see it. With, for this example, the two sides being different due to the gloss. We'll always recommend 45-0 specs. My colleagues can feel free to disagree with me here, but that's kind of a holdover kind of a legacy thing where we would never really recommend specs unless you have a specification you need to follow that is calling for specs measurement. 45 zeros better.
I agree with that.
Thanks, Ray.
One additional comment about that. Go back in history, and people would use spin and specs to estimate a gloss value. But in all of our instruments, we actually put in a 60-degree gloss meter to quantify it and measure it correctly. So there were some applications in years gone by where estimating gloss differences was used, but now you can either have a separate gloss meter or have built-in gloss meter with either geometry type.
Okay, thanks, Greg. If there's other questions too, or comments, or any challenges you're having at your own facility or with your own application, please log them in the Q&A box. We got some time here. Also, another question I have on my list, does the angle of measurement affect the readings on the Big Mac Multiangle?
If you're referring to the orientation of the instrument on the painted surface, the answer is yes.
Yes. Okay.
So, yeah, so by design, multi-angle spectras have a directional light source, meaning it does not have circumferential illumination like the 45-0 does. And the reason for that is those products that you're typically going to use the Big Mac on are most often seen outside under daylight, and even if they're not, even if they're inside, the light's pretty much always going to be coming from overhead. And because of how directional those pigments are, I mean, you can see different things from different angles. You want that directional light source to mimic what you're seeing. You don't want to wash that out by using circumferential illumination in that case with those effect pigments. You want to be able to tell the differences at the different angles. And so for that purpose, yes, it is directional, and the multi-angle is not circumferential.
Okay. And Ray, maybe this is a question for you. Is there a way to really standardize that to make sure, in the process, to make sure that orientation is consistent from operator to operator and over time? Or what's the procedure there?
So we always make sure that when we install the instrumentation that we explain the importance of this, because we had an incident at one plant where one guy on the day shift was measuring with the instrument in the proper orientation, and the other guy was measuring it at a 45-degree angle compared to the proper orientation, and they were getting completely different numbers. So it's totally important, and we try to stress it as much as possible. I know Greg does too. We always want to make sure that we measure with that arrow that's on the side of the instrument going down, because you know the light source is coming from the top. And there's two green LEDs on the top that also tell you where the light source is coming from. So that's hugely important. I mean, Greg probably has some comments too.
I agree. It's important.
Good comment, Greg.
Yeah. And not just for not just for a harmony type of situation, but it's really important when you're formulating.
Sounds good. Sounds good. I have another question here. Do we have other webinars specific to the Spectro 2 guide? I don't know offhand in our schedule, but I have a note of your name and your question, and I'll have one of our field people or Corey reach out to you. And
so I would say go to our website, byk-instruments.com. We have some webinars recorded on our website. So if you go to that section, I actually did one on the Spectra 2 guide maybe a month ago, and it should still be up there. Look there for it. It's called color control and prediction of color stability. I think it's on the fluorescence aspect of the Spectra 2 guide, as well as the we talk about digital standards there.
Can you unmute? Can you unmute them for a second?
Yeah. Yeah. Let me find your name. Here we go. All right, Awilda, I'm sorry if I'm mispronouncing your name, but you are unmuted. Would you mind expanding what exactly you're looking for?
Oh yeah, we have Spectra guide and Spectra 2 guide, and I manage the lab, so I don't use the instrument, but I would like to know more about the instrument and any available training resource.
So do you want training like on the software too for the Spectra Guide 2 for like Smart Chart?
Yeah.
I mean, if you want, like, we can send you something and you can just ask somebody to come in and we can do it on site for you, or we could do a special one just for you guys if you like.
Okay, thanks.
Okay, so we'll get in contact with you and we can go from there. Okay, thank you. Let me mute you again here. There we go. And also note, in the follow-up email with this presentation and the recording of this, at the bottom of the email, you'll see future webinars, both in our office hours format, which is what we're doing today, and then also in just our standard format where it's a longer presentation and shorter Q&A with that.
There's
another question here from Jose. Is there a faster way to compare deviations to a standard with multi-sample readings? He usually does this manually, and it's very time-consuming. Definitely.
Yeah, so with our software, or even just in the instrument itself, you can store a standard. You can measure a standard and save it in there, so that you can pull it up anytime you want, and then just take a sample measurement, and it automatically calculates it for you. So it's our software in particular is very versatile as far as that goes, where you can take a bunch of sample readings, you can take a standard reading, and pair them up and look at the differences all together. You can actually change the difference method to see what it would look like under, for example, Delta E star versus Delta E 2000 or Delta E CMC. So yeah, it's all very easy to do, the software.
Awesome. We have a question in here from Rong. Is there an instrument appropriate for measuring the whiteness of a tooth?
Interesting. So
that's a good. You may have one stumped the Corey, Ron. We'll see.
Hey, could you use the Spectra guide and use one of those holders for like cosmetics?
Yeah.
Or just you're like actually like on a physical tooth, like in someone's mouth tooth.
Ron, I'm going to unmute you if that's okay here. Are you there, Ron?
Yes, I mean, yes. Thank you very much. So, I mean, at this point, just maybe like in vitro, not in vivo. Not in somebody's mouth, just measuring it like on a table.
Yeah, so we have like some sticks for fingernail polish. I don't know. Does that work for the Spectra too, Corey? I can't remember.
Yeah, I mean, the size would certainly be the problem. So we have a small Aperture model in our color guide instruments. So that would probably be your best bet. It's a 4mm Aperture, so you should be able to measure a tooth with that. I'd say any other instrument, the Aperture would be too big for measurement.
Okay. So the problem will be the Aperture will be too like bigger than the actual tooth, right?
How big?
Yeah.
Right.
Okay, I see.
Yeah.
The color guide 4mm would probably work, but you need a fixture to put the tooth in the same spot, or as best as possible, the same spot every single time. And teeth are translucent. So you have to have either a consistent covering or some type of consistent backing. So you either want to put like some type of black, we have like a black cup or a black trap you could put over the instrument to block out any light that would affect the measurement too.
Okay.
And
Okay.
we can
We can follow up.
testing on that too, right, Greg or Corey?
Yeah.
Yep. Okay.
Thank you.
All right. Thank you. Okay. Any other questions here in the remaining few minutes?
So I do want to
Is
mention
there-
that we have a new instrument called the Spectra 2 Profiler that is also a color measurement instrument. It measures with a 45-0 geometry, just like the Spectra 2 guide, but it also measures surface texture. Surface texture and what we call reflectivity, because gloss is very difficult to measure on textured surfaces, and quantifying and matching the pattern, the texture in two different surfaces is very difficult. So we have an instrument called the Profilers, the Spectra 2 Profiler, that measures color, reflectivity, and surface topography to match up different textures. And so if you're interested in hearing about that, I didn't cover it today, but if you're interested in hearing about that, we are doing a 1-hour web seminar next week that you can sign up for on our website.
Yes, and you'll get that link in the follow-up materials. It'll be towards the bottom where it lists all of our web seminars and office hours formats. So you'll be able to sign up and register there. I think it's on the 25th, I believe. So I think that is all of our questions. Thank you very much for your time. Thank you, Corey, Greg, Ray, anybody else that chimed in. We really appreciate the insights. Oh, one more question. Just snuck in under the wire, Jose. Nice. High reflectance and low gloss coats are popular. What makes them different? I'll read it again. Yep, and low gloss coats are popular. What makes them different?
Are you so high reflectance meaning white colors, light colors? Is that what you mean?
Let me see, Jose. I'm going to unmute you here. There
Yes,
you are. Are you there, sir?
It's a new pigment. So I'm wondering if if the instrument has capability of reading this pigment.
Yeah, I can't imagine it would have any difficulty with that. Just keep in mind that if you're dealing with differences in gloss level, that will be reflected with the 45-0 instrument.
Okay.
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 Does that help, or did that answer your question?
Yes, a bit. Yeah. It's a new subject for me. Okay.
No, that's okay. That's okay. We can have someone reach out to you too, and make sure all your questions are answered thoroughly with either a WebEx or phone conversation, or even on site also. Okay. All right. Thank you, sir. We appreciate it. And thank you, everyone else, for attending this edition of Office Hours. Please look out for the follow-up materials tomorrow morning, and stay tuned for other invites to Gardner web seminars. Thank you very much, and have a great rest of your afternoon. Bye-bye.
Thanks, everyone. Bye.